Hey everyone. So I just wanted to, I know we sort of ran out of time at the end of class and I was rushing through this. So I just wanted to make this very, very quick. I'm going to try and make it short. Just follow up to what we were talking about. Okay. So this is sort of where we left off right here. And I just want to show you, I sort of skipped this one right here, this orbital diagram, this guy right here. But I just wanted to show you, this is just a different way to show an orbital diagram. So if I was going to do carbon, I could do the same thing as what I did right here. I could just do it with this orbital diagram. So it's 1, 2, 3, 4, 5, 6 electrons in that orbital diagram for carbon. It's the same as what we have here. It's just written differently. I prefer this one because it's a little easier to write out. Okay. We did do a few of these. So phosphorus, same thing. 1s2, 2s2, 2p6, 3s2, and then 3p1, 2, and 3. So we have to fill those singly before we go back and double them up. Bromine, we'd have to add in some extra boxes here. So we'd have to add in like a 4s right here, and then we'd have to add in a 3d. Well, D has 5 boxes. Let me just do it this way. 1, 2, 3, let's see, 1, 2, 3, 4, 5. Then we would go 3D, and then P's, there's 3 of them. This doesn't look very good, but we'll just go with it. 4P. So then we can just keep adding arrows until we get to 4P5, which would be 1, 2, 3, 4, and 5. Okay, so again, this chart right here is going to be, we won't be able to do it without that chart for now, but we'll get to the point where we don't need that anymore. But for right now, we're going to lean on that chart. Okay, the last thing I want to show you is valence electrons. So you may have heard this term before. Most people are familiar with it. Here's our valence electrons for antimony. It's the outer ring or the outer energy level electrons. So antimony has 5 valence electrons. Silicon has 4 valence electrons, those 4 outer electrons. So these guys are called valence electrons. Everything else is called a core electron. So everything that's not valence is a core electron. Here's another example right over here using electron configuration where these are our core and these are our valence electrons. So the question is, well, how can I tell just by looking at an electron configuration where my valence electrons are? That is a great question. So remember, when I draw this out, like this is energy level 1 or ring 1, and here's my 2 electrons in that first ring. This is ring 2, that coefficient of 2, and here's my 6 plus 2, here's my 8 electrons that are on that second ring. Here's energy level 3, and here's 2 and 2. So there's 4 electrons in that third energy level. So the valence electrons are always going to come from the highest coefficient. Okay, that's why down here when we have 28 electrons, it's not always at the end. It just depends on where's my highest energy level. So there's energy level 4, and there's energy level 4, and there is 2 electrons in here and 4 here. So that gives us 6 valence electrons. Okay, and everything else is our core electrons. All right, so how do we figure this out? Let me just show you 3 and 4. Well, I'll show you magnesium first. So magnesium has 14 electrons. So I'm going to write this out. 1s2, 2s2, 2p6, 3s2, 3p, what is that? 10, 12, so I need 2 more, that's 14. Okay, so now I have 14 electrons. Again, my valence electrons are the outer ring electrons. So this 3s2, there's 2 electrons on ring 3. There's another 2 electrons on energy level 3. So I have 4 valence electrons total. And everything else would be our core electrons. Okay, so now we can also do this with ions. So remember zinc. Zinc has 30 protons, just based on the periodic table. And if it's neutral, it's also going to have 30 electrons. But it's not neutral, it has a positive 2 charge. So that means I actually lost 2 electrons. So my total here now is 28. It's not 30 anymore because my total charge is positive 2. So I need to account for 28 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. This is where it gets a little strange because 4s2 actually comes before 3d. It's weird, but that's just the order that we notice when we follow this little arrow chart. And there's a reason for it, but instead of memorizing it, we just follow the chart. Okay, and then I think we have 20, so we just add an 8 right there, and now we have 28 electrons. Right, so I can just add up the exponent, excuse me. Now, valence electrons. Energy level 4 is the highest ring, it's the highest energy level, and there are 2 electrons, so I have 2 valence electrons, and everything else, those are called core electrons. Okay, I'll do one more. Iodine. Iodine has 53 protons, so the neutral iodine is going to have 53 electrons. But now it has a -1 charge, so it's actually gained an electron. So now it actually has 54 electrons. So what does that look like? Here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Here's where we get into some weird overlaps. 5s2, 4d10, 5p. Normally it would be 5p5, and that would add up to 53. But because I've gained an electron and now I have 54, I just add one more and it becomes 5p6 for the ion. Okay, valence electrons. I have energy level 5. I have 2 electrons here, and I have 6 electrons here. So I have a total of 8 valence electrons, and everything else is a core electron. All right, uranium. If you're a glutton for punishment, or you just think these are fun and you want to try it, you can try and write all the electron configurations for uranium. I will just tell you it should end with 7s2, 5f. I gotta look at my periodic table. 1, 2, 3, 4, 5f4. So it will end with that. You got to do all the rest. 1s2, 2s2, 2p6, and all the rest of that stuff. But you should be able to tell the number of valence electrons and core electrons. I hope that